just try and review what we had done. So we have like a, can everyone see my screen?
Yes, Professor.
Okay, so we talked about the fact that we might have a set A and a set B, and we use the symbol N of A to indicate the number of elements in A, or similarly the number of elements in G. I guess it says G. We said, and we had an important definition. We said events are subsets of the sample space. So remember, the sample space is the set of all possible outcomes when you do an experiment. We had these words: experiment, sample space, event. And we talked about the event of rolling a die, the event of tossing a coin, the event of tossing 2 coins, the event of tossing 3 coins. And each time we write out what the event would be. So when we toss a coin, it's H and T. When we roll a die, it's 1, 2, 3, 4, 5, 6. When we roll 2 die, it's H, 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 T, T, H, T, T, and so on. And then we talk about events. And events are subsets of the sample space. So here's a subset of the rolling die sample space. And maybe you call this the even numbers, or maybe you call this one the odd numbers. Events are subsets of the sample space, and we use this symbol to indicate how many elements there are. And we remember that the concept of subset is means that every element in this set is in this set, and so this is a subset. Since it's this is a set, it's a subset of this, so therefore we can call it an event, even though maybe it doesn't have a nice name like even number or odd number. It's still an event. We could just say it's the event of getting a 1, 5, or a 6. Okay, and then we have, for another one, the event that you get a number less than 4. Or when you toss 3 coins, talk about that experiment. Here's the sample space. We could talk about the event of getting 2 tails. So that would be, this has 2 tails, this has 2 tails, and this has 2 tails. And then we can talk about the probability of getting exactly 2 tails. So how do we do that? How do we get that? And we said that, well, we looked at this problem first. We said, what's the event of an even number? And that was 3. We say it's 3 out of 6, or 1/2. And so we realized that to measure probabilities, we can use a very simple formula, which is just to count how large the event is compared to the size of the sample space. So this would be 3, and this would be 6. So we would say the probability of this event, of getting the even number, is 3 over 6. And so we have 3 over 6. Or we can have a different event. I guess H is just getting a 4, and the probability of that is just 1 over 6, so 1/6. And so here's the definition we're going to use in this lecture for probability. It's just this. Okay, now suppose that we have, let's see here. Suppose that we have an event, say G is 1, 2. We have an event H, which is the event 5, 6. So what we can ask, what is E union F? E union H. Sorry. What is G union H? So can somebody give me that?
It's 1, 2, 5, and 6.
1, 2, 5, and 6. Okay. So suppose that I want to know what is the probability of G union H. Well, we already said that the way to do that is to write N of G union H over N of S. Right? Everyone understand that?
Yes, Professor.
Okay. But we might say, well, I think it should be equal to, without sort of going through this, I think it should be equal to the probability of G plus the probability of H. Why, it sort of looks like, probability of G union H, but you should be able to just break it up and say it's the probability of G plus the probability of H, right? So we can say, well, let's check and see if that's true. Well, this and G union H is up here, and there's 4, so this has 4 on the top, and the bottom has 6. So, okay, that's that side. Now, how about here? What's the probability of G?
Two out of 6.
Okay, and what's the probability of H?
2 out of 6 as well.
So, yes, it's true, right? It works, right? The probability of G union H equals the probability of G plus the probability of H. Everyone agree? See that?
Yes.
Okay, so that's nice, right? That's a nice nice result. Now let's say that we had G was what did we say G was? 1 and 2. Let's say we have K is equal to 2 and 5. Okay, let's check it again. The probability of G union K equals the probability of G plus the probability of K. Right? So this is, we already did this. So, oh no, sorry, we didn't do this. What is G union K? G was what? G was 1, 2, and K is 2, 5. So G union K is what?
1, 2, and 5.
1, 2, 5. Okay. So the probability of G union K is what? 3 over 6, right? Okay, now how about here? Probability of G is what?
2 over 6.
G is 2. Has 2. So this is 2 over 6. And K is also 2 over 6. No. Doesn't work this time. Okay? Everyone see what's going on here?
Yes.
The first time it worked. Second time it didn't work, right? This time it worked. This time it worked. But this time it doesn't work. So why didn't it work the second time? Let me write G. What was G again? 1, 2. Okay, and where's K? Here's K. And what was H? H, I think, was 5, 6. So why didn't it work this time?
Because both G and K has 2.
Oh, because both G and K have a 2. Yeah. So because they have some intersection, right?
Yes.
And why does that make it not work? Because when we count the probability of G here, in our calculation here, we count the probability of G, we get what? We get 2. Well, I'm just going to say 2. I mean 2 6. We get 2 here, and we get what here? For K, we also get 2, right?
Oh, yeah.
We have 2 from G and 2 from K, right? Everyone understand that?
Yes.
So we're counting, in other words, we're counting that this 2 twice. We're counting it when we say we're getting 2 6 here, we're counting the 2 once there. And when we're counting 2 6 here, we're counting that 2 once here also, right? Does everyone agree with that?
Yes.
Right? But when we do it with G union K is here. How many times do we count the 2 for G union K?
2 times.
Only once. So why should they shouldn't be equal, right? If we count the 2 only once here, but we count it twice here, not going to be the same, right? So they're not equal in this case. But we could adjust this by taking out, by taking out the thing that we counted twice. We could take it out once. So then it would bring it back just to counting it once, right? If we counted it twice and then we took that out one time, then we'd only have counted it one time. So that is, if we take out the intersection of G and K. Now it's going to work, right? Because what is the intersection of G and K? What is the intersection of G? Where is G? G and K?
2.
2. And what's the probability of 2? Well, sorry, this is 2. And what's the probability of that? 1 6. 1 6, right? So now it's going to work, right? Now it's 2 plus 2 minus 1 is equal to 3, right? So, okay, we have this rule. Probability of G plus the probability of K minus the probability of G intersect K. Okay? Now, if we know for sure that G and K have nothing in common, then we don't have to have this extra piece, right? Because then it worked before, right? Up here, where was it? Here, it worked, right? When G and H had nothing in common, then we didn't need that extra piece over here, right? Everyone agree? Right? Here we got 4 6 and 4 6. We didn't need that extra piece. Why? Because they had nothing in common, nothing in their intersection. So if we know for sure that G and K have nothing in common, then we can write what? We can make it a little shorter. We can write what? The probability of G union K equals just the probability of G plus the probability of K. We don't need the last term, right? Everyone follow that?
Yes, sir.
So if we know for sure that G and K have no intersection, means G intersect K equals the empty set. If we know that their intersection is empty, then we can say this. Okay? So we have two versions, this one and this one. If this one only works if the intersection is empty, This one works all the time. Okay? All right, so we've done that. All right, now, what else? Okay, so now I want to, that's one rule. There's another rule. We have to talk about the complement of an event. Okay, the complement of an event. So let's take G, for example. Take G. Or okay, so we're going to talk about something called the complement of an event. We're going to denote it by either G with a bar on the top, G with a C there, or G prime. Okay, so let's take our event G, which was G was 1 and 2, I think. And what was the sample space? What was the sample space? Nobody? Nobody remembers the sample space?
Yeah.
What is the sample space here?
Six.
What?
What was it? 6?
I say that again, I can't hear you.
6.
6? The sample space is, anybody remember?
Was it 1, 2, 3, 4, 5, 6?
1, 2, 3, 4, 5, 6. Okay, so let's make a picture of this. Let's do this. So let's say the sample space is here. And let's have G is here. So G, so the sample space contains all, all the points, but G contains 1 and 2, and then in the sample space we have 3, 4, 5, 6, right? Okay, does everyone understand this picture? And this set here is called the sample space. That's the whole set of outcomes. Okay, now the complement of G is everything outside of G. In S, which is not in G. Okay, so what is the complement? Let's use this for the symbol, G complement. So what is the complement?
3, 4, 5, 6.
Okay. And what is the probability of G?
Two over 6.
And what is the probability of G complement?
4/6.
And if you add them up, the probability of G, what do you get?
1.
1.
Right. Now, how about if we had this picture and we had, let's make two more here. Okay, and let's call this one A, this one B, and this one S. Okay, so let's say A is 1, 2, 3, 4, 5, 6. Okay, so A is what?
One, 2, 3, 4.
And B is what?
4, 5. 4, 5.
Okay. Okay, good. Now what is A complement?
6. 5, 6.
5, 6. Okay. What is B complement?
1, 2, 3, 1, 2, 3, 6.
Okay. So what's the probability of A?
4 over
4 out of
6.
6.
Probability of A is what? 4 over 6. And what's the probability of A complement?
2 out of 6.
What's the probability of A plus the probability of A complement?
1.
1.
1. And how about what's the probability of B? 2 out of 6. What's the probability of B complement?
406.
What's the probability of B plus the probability of B complement?
1.
1. This is always true. For any event, the probability of A plus the probability of A complement is going to be 1 because A means everything in A, and A complement is all the rest. So when you add everything up, you have to get 1, right? Does everyone understand that?
Yes.
By the way, what's the probability of S itself?
1.
1, because the definition of that would be this over this again. Because this is always on the bottom, and then we put this on the top, so we get 1. The probability of the whole thing is 1. Okay, so we have this rule for any set B, right? Everyone agree with that? Which we could rewrite like this. The probability of B complement equals 1 minus the probability of B. Everyone see that?
Yes, sir.
Okay, the probability of B complement is 1 minus the probability of B. All right, so that's a rule that we want to have. So we have kind of 2 or 3 rules, right? Several rules. This is one of them. Okay, the probability of B equals 1 minus the probability of B complement. Okay, now we finished all the basic stuff. Now we want to talk about conditional probability. And I think we also need to talk about something called independent events, but maybe that will be in my slides. But anyway, conditional probability. Okay, So how many people have studied this before? Let's see. Raise your hand in the, how do you do it? In the, wherever you raise your hand, if you studied this before, conditional probability. All right, well, probably most of you have, but let's review it. Okay, so let's suppose that I roll a die. I'm rolling it on my table here in my room, but you are not here, you are in your rooms, so you can't see what happens. So I roll it, and I drop it on the table, and I look at it. And then I tell you it is even. Oh, sorry, before I do that, if I just ask you, what's the probability of getting a number no, let me say, what's the probability of an even number?
3 out of 6.
It's 3 out of 6, right? Okay. Okay, I'm not going to tell you it's even, actually. I'm going to tell you that it's greater than 3. So I tell you that it's greater than 3. So the result is greater than 3. So everyone understand the scenario? First of all, I asked you what's the probability of even. Everybody knows that. Then I said I roll a die, and I tell you that, and I look at it, and I tell you it's greater than 3. Everyone understand? Okay, so let's just draw a picture. So let's suppose that we have this, and we have the numbers 1. We have 1. Why can't I write 1? Oh, 1. 1, 2, 3, 4, 5, 6. Okay? All right, those are the numbers. Now, I roll it, and I tell you that it's greater than 3. So that means I'm telling you that it is here. This is the event, right? Everyone agree with that?
Yes, sir.
Okay, so I know that this, let's call this event greater than 3, let's call that F. So I know, I'm telling you that F has occurred. Now I ask you again, what's the probability that it's even? So after I roll it, and then I tell you that F has occurred, I tell you that it's greater than 3. Now I again ask you, what's the probability that it's even?
2/3.
2 over 3.
How many people, let's see, let's have a poll. I should edit. No, that was wrong. Why is it not working? Okay, so let me try this again. No, sorry, that's wrong. Let me try edit. Okay. Try it again. Let's see. That didn't work. I can't do it right now. It takes too much time. Not a very good system. Okay, so how many people, raise your hand if you think it's 2 out of 3. Okay, now raise your hand if you think it's something else. Okay, Evanita, what do you think it is?
I think it is 2 out of 3.
You think it's what?
2 out of 3.
2 out of 3. Okay, all right. I think it's 2 out of 3. Why is it 2 out of 3? We already said that it was 1/2 or 3/6, not 2 out of 3. It was not 2 out of 3, right? Probability of even is 1/2. But now, if I tell you that the number is greater than 3, this is the event F, now you want to change your answer and say the probability of even is 2 out of 3. Okay, I think, okay, I agree with that. Now how I want to rewrite this question, because just saying this is not very good, because the probability of even is 3/6, not 2 out of 3. So this is not, I didn't write the question properly. So I want to rewrite the question. So the question was the probability of even given that F occurred. And that is 2/3. So that's not, the probability of even is not 2/3. We shouldn't write that. We should say the probability of even is 1/2. But the new question was the probability of even given that F occurred. Does everyone understand there's a difference in these two questions? This question is not the same as this, right? Does everyone agree with that?
Yes, sir.
Yes.
Okay, so does anybody know a better notation for the second question instead of having to write this whole thing out like that? Probability of even is not too bad, or we could call it we could call it even. Oh, where is even, by the way? Let's say even is here. Even is here. That's E. And the probability of E, we already said, is 1/2. But that's not what we asked here. So can somebody give me a better way to, the standard way to write this question?
You
Yes.
write P and then even and then a straight line and then F.
Okay, right. So this is just a shorthand for this. The probability of even, given that F occurred, we can write that just like this. So this does not mean that straight line has nothing to do with divide, has nothing to do with divide. It's just straight line. It means given that. So it's the probability of E given F. Okay? So that's what that means. And the answer to this is correct, 2/3. Okay, so why was it 2/3? So most everybody got the number right. So why is it 2/3?
Uh,
What's the answer?
Isn't it because there are 3 even numbers and there are 3 F numbers like in the F, and 2 of them are even.
Right, that's right. So when we said given F, right? That's part of what we said. Given F, right? When we said given F, that means now we're stuck in the green box now. We can't be outside the green box. So when we say given F, that means essentially the new sample space is F. Okay, does everyone agree with that? So that's the only set of things that can occur are within F. So now once we're in F, how big is the sample space, the new sample space?
3.
3. And within that new sample space, how many are there?
2.
2. Okay, so that's how we can show that it should be 2/3. Okay, does everyone follow that argument? So how could we could rewrite that like this? We could still say, we could write it as the size of this, that is the size of F on the bottom, that's the size of the new sample space, and then we can't write on top N of E. Why not? I can't put that here. Why not? Because the N of E is what?
2, 4, and 6.
N of E is 3, right?
Yeah, 3.
Right? That's not right. We can't put 3 there. That's not right. So what do we have to put there? In terms of the symbols.
The intersection between E and F.
Yeah. We want N of E, but not all of E, only the part of E that is in F. Right? Does everyone agree with that?
Yes.
Okay. So we can say now that the probability of E given F equals that, N of E intersect F over N of F, right? Now, of course, everybody knows that if I have 2 numbers, A and B, and I have a fraction like that, I'm allowed to divide both of them by C, right? It's still equal to that, right? A over B is equal to that, right?
Yes.
So I can divide this and this by the same thing and it won't change the result, right?
Yes.
So I can divide, for example, this by that and this also by that, right? It doesn't change the calculation. Okay, so can you read me the bottom of this? What is that? Can you give me another name for that?
It's PF.
Right. It's P of F. Okay, everyone agree with that? This is P of F, right? This is the probability of F. If I ask you what's the probability of F, you should say N of F over N of S. Okay, and what about the top part? Can you give me another name for that?
E intersect F.
Okay. Okay, so now we have our definition for what we call conditional probability. So the probability of E given F is equal to this. Okay, does everyone agree with this? So whenever you're asking a question like this, one thing given another, you do the calculation like this. Okay, everyone happy with that?
Yes, Professor.
Okay. Okay, now I think we can go to our slides. Okay, so the basics are sample space, event, and we're not doing R, so we don't have to worry about that. Okay. Not doing this. Okay. We're not doing that. So if you want to learn this in the context of R, you can buy my new book. Okay. All right, conditional probability. So here's the definition of what we just said, right? Does everyone recognize it?
Yes, Professor.
Conditional probability. Probability of A given B is the probability of A intersect B divided by the probability of B. Okay, so let's try it out. Suppose we have two boxes. Well, not let's try it out, but let's use it. Suppose we have two boxes. One is green and one is purple, and they both have balls in them. They both have balls that are blue and yellow. How many blue boxes? I'm sorry, how many blue balls are in box 1?
4.
And how many yellow?
8.
8.
8. Okay, and how about in box 2? What is it? Is 2 blue and how many yellow?
10.
10.
Okay. Okay, good. Suppose we have two boxes. Box 1 is green and has 4 blue and 8 yellow. Box 2 is purple and has 2 blue and 10 yellow. Suppose we select a box at random and then select a ball at random. So that is our experiment. Okay, does everyone understand? We're going to do this experiment. Suppose we select a box at random and then select a ball at random. So when I say select a box at random, what does that tell you? Anything?
Either box 1 or 2.
What?
Either box 1 or 2 randomly.
I'm sorry, I can't hear you.
It can be either box 1 or 2.
Yeah, and it tells you a little bit more than that.
The probability of selecting box 1 or box 2 is 1/2.
Yeah, can I write on here? No, I guess not. Why not? Why can't I write on here? That's not good.
I think you need to click the thing on the bottom left corner, like the pen or something.
Oh, yeah, I don't have that. It's really bad. We'll have to learn how to do that some other time. I can't do it. No, it's not letting me do it. I'll have to figure that out. Okay, anyway, so it means that I can do it if I do this, I think. Let's see, can I do it here? Oh, I know why. I think I have to go here. Well, anyway, I can do it here. So it means that the probability of box 1 is what?
Half.
Yeah. And the same with box 2, also a half. Okay. Let me just try that again. Can I write now? No. Okay. Suppose we select a box at random and then select a ball at random. Then we can ask questions like the following. A simple probability question might be, what is the probability of getting a blue ball given that we selected box 1? So what is the answer to that?
4/12.
Yeah, I think that's right. 4, I think there are, what did we say, 8 yellow balls? So it would be 4 out of the total number, which is 12. Okay, so does everyone agree with that?
Yes.
4 out of 12, I can't write. Okay, this can be written, this question can be written like that, right? Given that we got box 1, the probability of a blue ball, right? Everyone agree with that?
Yes.
A more confusing question might be, what is the probability that we selected box 1 given that the ball is blue? Does everyone think that's more complicated? Does everyone agree that that's a more complicated question? Or it's a more complicated answer?
Yes, I think it is.
Yeah. The first one was very easy to do. We just said it's 4 out of the 12, but this is different, right? This is, what is the probability that we selected box 1 given that the ball is blue? Before, we were given that it was box 1. Here, we're given that the ball is blue, right? So, and that seems harder to answer than the first one. How do we write this second question, though? Not how do we answer it, but how do we write it? Can somebody tell me how to write it?
It's P box 1 straight line blue ball.
Okay, good. P box 1 straight line blue ball. So just the opposite of what we had up here, right? This is just the opposite order here. So given that the, probability that came from box 1, given that the ball is blue, is written like this, right? So that's harder to calculate. Given that the ball is blue, how do you know, what's the chances that it came from box 1? That seems kind of tricky to do, right? The question is difficult to even think about how to do it because the order of the events is mixed up. Because the procedure that we're doing is we're first selecting the box, then selecting the ball, but here it's reversed. They're saying, given that you have a ball, a blue ball, what's the probability of the box? So the procedure is kind of mixed up. First select the box, then select the ball, but here we are saying, suppose we have a blue ball, what is the probability that it came from box 1? So the order of the events is kind of mixed up. Everyone understand what I'm saying?
Yes, Professor.
So the order can make the question confusing. This is not confusing, given that it comes from box 1, but this is confusing, given that it's a blue ball. So we have something called Bayes' theorem that will allow us to reverse the order if we want. So instead of answering the confusing one, which was this one, I think, we can reverse the order and answer and sort of use that calculation to answer this question. Okay, does everyone understand what I'm talking about? Okay, so that's what Bayes' theorem will do for us. So this is Bayes' theorem. So here at the top, on the left side, we have the probability of some A given B, right? So everyone see that? So this might be box 1 given blue ball. Okay, everyone understand?
Yes.
So this is tricky. We don't really know how to go about answering this. But Bayes' theorem, if you look at what's on the right-hand side of Bayes' theorem over here, do you have A given B on the right-hand side?
B given A.
Yeah, you have B given A. So it allows you, you can see, to change from A given B to B given A. Okay, so it might make it easier to do it. Now, of course, you have to do some extra work. You have to also calculate this and this if you use Bayes' theorem, but it may all in all be easier than having to do this. Okay, the conditional part is this, which might make it a lot easier, and then calculating this and this might not be very hard, so the whole thing might not be that hard. Okay, does everyone understand the idea? So this is Bayes' theorem. Notice that we have that on the left side we have A slash B, but on the right side we have B slash A. Of course, there is more on the right side than on the left, but the conditional part is reversed, and that's what we wanted. So how does this help for the question earlier? That is, how does it help the probability of box 1 given that it's a blue ball? So if we follow this, how would we rewrite the question now? How would you say it in English?
Isn't it like it equals the probability of the smaller box? The probability of blue balls in the smaller box, and then times the probability of blue balls, and then over probability of the blue balls overall.
So
I might be wrong.
So what is this going to be for our question? So you're gonna have to give me 3 pieces. This piece, and this piece. So what are they? What is this one for our question? So here's our question here. So what is this piece for this question?
Probability of blue ball given box 1.
Blue given box 1, right?
Right.
That's really bad. They're both BL. Let me write it up here. Probability of blue given box 1. Okay, that's good. We got that. Was the hardest part. That's here. And then what's this one?
All blue balls.
Box 1.
I think that's the probability of box 1, right?
Yeah, sorry.
Right?
Yes.
Yeah. Probability of box 1. Okay, and on the bottom?
Probability of blue balls.
Probability of blue. Okay, now maybe this is not easier, but maybe it is. Just because you have something equals something else doesn't mean you have to use this. Maybe this is easier to do for some reason, or maybe this is. So, we just have to, but we at least have the option of doing it this way. Anyway, and doing it this way is this. So how about this? Is this hard?
No.
This is easy, right? What was it? Blue, I think there were 4. I think it was 4 out of 12,
4
right?
out of 12.
Okay, that at least was easy. What about the next one? Box 1. Remember we said at random. So what does that mean?
Half.
Half. Okay. And then blue is a little bit tricky. Blue isn't that much easier than the original problem. But how do we get blue?
6 out of 24.
We take the total number of balls
24.
and the total number of blue, right?
Yes.
So what was the total number of blue? I don't remember.
6.
6, okay. I'll take your word for it. 6 out of 24. So maybe maybe this is, so I think this is right. So it's going to be this times this, sorry, this times this over that. Okay? So that gives us one way to do it. And anyway, so this is what Bayes' theorem does. Does everyone see what Bayes' theorem does? What I usually say, there are many ways to express the meaning and value of Bayes' theorem. Mine is maybe the most mundane way to say it. People have much more sort of interesting ways to say it, but I'm saying it as all it does is it allows you to reverse the order of a conditional probability. Okay? Does everyone understand that?
Yes.
Okay. Now there's much more, there's a whole science called Bayesian Statistics, which is based on this theorem. And and they don't express the fact that the Bayes' theorem is just the fact that it allows you to reverse the order. That's not how they say it. What I said is true. That's what it does. It allows you to reverse the order. But there's a whole way to interpret it differently, and maybe we'll get to talk about that. But right now, I'm just saying that. Okay. So how does this help us do the question earlier? This question, it is all there. Everything is here, except the denominator may not be that clear, we said, but we found the denominator, 6 over 24. We will prove Bayes' theorem next and rewrite the denominator in a way that makes it easier to calculate. Well, we already calculated it, but we're going to rewrite it anyway. Maybe that will make it even easier to calculate. Okay, so here we have a picture of a sample space, which I called U, or the universal set, but it's just called U. And we have 3 events. Can you see the 3 events that I'm referring to? Because remember, I mean, you could say there are more than 3 events, but there are 3 main events here. And remember, what's the definition of event? What's the definition of event? What is that?
Subset of F.
Subset. Okay, so we have, I say we have 3 events here. What are they? So the sample space is U. What are the events that I've drawn? You could say there's more than 3, but I think there are 3 main ones.
A intersection B, complement of A.
What did you say? I didn't hear you.
A intersection B.
Okay, that's not what I meant. My question wasn't very good. Okay, anyway, there are 3 events. A complement, and B.
Yeah.
Okay?
Yeah.
You could say this is also an event, and this is also an event. Okay, that's fine. But anyway, does everyone recognize these 3 events? There's
Yes.
A complement, and B. Because each one of those is a subset of the sample space, right?
Yes.
Now, we can break up B though. B is this oval. We can break it up into the union of 2 other events. What events?
A and A complement.
Well, yeah, but I mean, A intersect B is where? Is here, right? This is A intersect B, and this piece here is what?
A complement intersect B.
Right. A complement intersect B. So B can be written as the union of this piece and what? This piece. Everyone agree with that?
Yes.
Okay, so B equals A intersect B union A bar intersect B, right? Okay. Now, and by the way, do these two sets have anything in common? Does A intersect B and A bar intersect B have anything in common? Does this have anything in common with this?
No, because A and A complement are complementary.
They're disjoint, right? We use the word disjoint. Means they have nothing in common, right? So you're right. So A and A complement are disjoint. So A intersect B and A complement intersect B have nothing in common, right? Does everyone see that? Everyone see that? Now, remember that we had something just maybe 30 minutes ago or less than that, where we said the probability of E union F was equal to the probability of E plus the probability of F. Do you remember that? Do you remember this statement? We did this about 20 minutes ago.
Yes.
But this was only true when? When E and F were disjoint, when they had nothing in common, right? If they had something in common, we had to amend it. We had to write it like this: probability of E plus the probability of F, then minus something, right? Everyone remember that?
Yes.
But if they were disjoint, we don't have to have this piece, right? We only need this, right? Okay.
Yes.
So going back to here, so this is B, is this and this, right? And I asked you, are these disjoint? These two are disjoint, right? So let's just make a note of that because, you know, that might be important in a few minutes. The fact that they're disjoint. Okay, does everyone understand?
Yes.
Okay. So we just said that. Okay, by the way, sometimes books will write, instead of A intersect B, they write A comma B. By the way, also, A intersect B, let's see, going back to here, sometimes, you know, A intersect B, how do I read this?
A intersect B.
Right, A intersect B, but you can also read it as A
comma B. Oh.
and B. A intersect B means A and B. It's the same thing. Like if you're talking about stat, like here's A and here's B, this is A intersect B. Those are the things that are in both A and B, right?
Oh, yes.
Right? So intersect and are the same thing, right? Everyone understand that?
Yes.
And then sometimes in text, they use this and they mean and, A and B. Now, in some texts, sometimes they actually mean or, which is really bad. I mean, it's really bad to have it could mean and or, but I think almost always, I have seen a few texts, unfortunately, where comma sometimes means or, but it shouldn't be. It should be and. Most books say it's and. So, okay, so sometimes comma means and, okay? And is the same thing as intersection. Okay, does everyone understand that?
Yes.
Okay, so let's go on. So sometimes we'll write A comma B for A intersect B, or A and B. So we had this picture before, and we had this. Recall that one of our rules of probability was that if A and B have nothing in common, that is, their intersection is empty, and therefore they're mutually exclusive, then we have the probability of A comma B, or probability of A intersect B, is equal to the probability of A plus probability of B. Okay, everyone get that?
Yes.
From the above, we get that the probability of the left-hand side is equal to the probability of the right-hand side, right? That's obvious, right?
Yes.
But these two things are disjoint. They don't have anything in common. This piece here and this piece here. So what can we do? We can change this union. Uh-oh, wait, now I made a mistake. Terrible. Oh. I forgot to correct this slide and I made a mistake. Okay, forget about this. This is wrong. Sorry. That is wrong. Can anybody catch what I did wrong here?
It's supposed to be union, not and.
What?
It's supposed to be A union B.
Yeah.
Not A and B.
Right. This is supposed to be the probability of A union B. So I shouldn't write it probability of A comma B if I just made the argument that comma stands for and, right? Because that would be A intersect B. So this is wrong here. Everyone understand?
Yes, sir.
Okay. So maybe I'll correct that before I show this again. Okay, so okay, this is okay so far. We didn't really do anything. We just said put a P here and put a P here. But now with this P, what can we do? These are disjoint. So this is A intersect B and A bar intersect B are mutually exclusive or disjoint. So we can change the union to the plus. So we get that. Okay, so everyone see that?
Oh, yes, sir.
Okay, everyone see that? So we can just, because these are disjoint, we're allowed to do the plus. We spent some time deciding that that was okay. So now we have the probability of B can be written like that. So with the above statement made clear, now we want to see how Bayes' theorem is derived and how it allows us to switch the order of A and B. First, recall the definition of the conditional probability of A given B. That is this, right? We just finished talking about that 30 minutes ago. That's the definition of conditional probability. So if you recall back here, I introduced that idea here. Remember we had this E and F, and we said given that F occurred, what's the probability of even? And we came up with the definition, after we did a little of this. Does everyone remember this? Okay? Everybody remember that?
Yes, Professor.
Okay, so now we're referring to that here. So that's here. So the probability of A given B is this. This is not Bayes' theorem. We haven't gotten to Bayes' theorem yet. Just reviewing our definition of A given B. Okay, first recall the definition of conditional probability of A given B. Next, we will move this P of B over to here, which of course we're allowed to do. So you get P of B, bring that up here, and that's equal to the probability of A intersect B. Okay, is that clear?
Yes.
And of course, the probability of A intersect B is also equal to the probability of B intersect A. That doesn't matter. So we can say that this equals this. So we can say that this equals this, right? Everyone agree?
Yes, sir.
Okay. So then we just have to do a little bit more algebra. We have this so far, that is this equals this. And now we go back to the definition of conditional independence, and instead of this, we're going to replace it with this. Okay, everyone see that? I'm going to take this piece. It currently looks like this or this, but I can replace this by this. So it's going to be, this is going to be on the top instead of this. And on the bottom, what did I do on the bottom?
You did the probability of B equal
Right.
that thing.
Yeah, this was probably a B, but we already did this before. We already know that we have the plus there and we have this, so we replace those. Okay, does everyone get that?
Yes.
Okay, and then what do we do? Okay, then we do one more nasty thing, and that is we can rewrite this. Really? How can we rewrite that? We can rewrite it like this. Why? Because the probability of A intersect B, probability of A intersect B can be rewritten like this, right?
Oh, yes, sir.
So we can put that down here. And then this one, we can also rewrite. Instead of having A intersect B, we can say A bar intersect B, and then we have to say A bar here and A bar here, and we get this. Okay? Everyone see that?
Yes.
And that is called Bayes' theorem. Now, we had another version of Bayes' theorem. We said it was like probability of A given B was equal to what? The probability of B given A times something over something, I forget. But this is another way to write it. Okay, and this might be a little bit easier to use, or maybe it's worse to use. But this is another way to write it. Okay, so this is called Bayes' theorem. So can we use this to solve the original question? So the original question is, given that it's a blue ball, what's the probability that comes from box 1? So what is A and what is B? If we're using this here.
A
What?
is box 1 and B is blue ball.
Right. A is box 1 and B is blue ball, right? So what are we going to have here? Blue ball given box 1. This is blue ball, I guess. Is that right?
That's box
No,
1.
sorry. This is box 1. This is blue ball given box 1 times the probability of box 1. This is blue ball given not box 1. So what does not box 1 mean?
Box 2.
Box 2 times the probability of box 2. Okay? So this might be a little bit easier, this bottom part, to do than the way we did it before. So somebody came up with 6 out of 24, which, yeah, it's true, but this is another way to get that 6 out of 24. Maybe it's easier, maybe it's harder. I don't know. I think it's easier, but some people will say it's harder. Okay. Now, one last thing is we had this picture before. Remember this picture? Sorry about that. There. Remember this picture? Everyone remember this one?
Yes.
Yes.
Okay. We divided the sample space U into how many black sets? In other words, ignore the blue one. Ignore the blue set. So we divided it into how many black sets?
2.
2, right? A and A complement, right? Everyone
Yes.
see that? Okay. This is called a partition of U. They say we partition U into 2 sets. In order for something to be a partition, so the partition I'm talking about right now is A and A complement. In order for that to be called a partition, it has to, when you put them together, it has to fill out U completely. And A and A bar do fill out U completely, right?
Oh, yes, sir.
And the other thing, in order to say that it's a partition, is that they have to all be disjoint, have nothing in common. So do A and A bar have nothing in common?
Yes, they have nothing in common.
Yeah, they have nothing in common, right? That's what we mean by A bar, the things that are not in A. So this can be called a partition, okay? So that's an example of what we call a partition, A and A bar. But we can go to that. So now we have how many sets there besides U?
4.
4. When we combine them all together, do we get all of U?
Yes.
Do these sets have anything in common?
No.
No.
Okay, so then this is also called a partition of U, okay? Everyone understand that?
Yes.
Okay, now let's throw in, so these are called a partition. We will say that the sets A sub I partition the set U if the union of all of them equals U and none of them intersect each other. So this is a partition. So the picture above forms a partition. Now suppose we have another set B like that. Okay, same kind of picture as before. So can we write B as something? Can we rewrite B some other way?
Is it A1 intersects A2, intersects A3, and intersects A4?
It's B intersect A1, B intersect A2, B intersect A3, and B intersect A4, right?
Yes.
Yeah, that's right. Before we had B was equal to A intersect B union A bar intersect B, right?
Yes, sir.
Right, that's what we had before. So what can we do now? So try to write B now. So that, or sorry. So we can write, we see that we can identify those regions, B intersect A1, B intersect A2, B intersect A3, and B intersect A4, right? And we can write B like that. Does everyone agree with that?
Yes.
Yes.
Okay, now, do these have anything in common? This, 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 and this?
No.
No.
No. They're all disjoint, right?
Yes.
So if I wrote the probability of this is equal to the probability of that, that's allowed. That's just saying the probability of the left side is equal to the probability of the right side. But now what can I do with the right-hand side? They're all disjoint, right? This, 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 and this are disjoint, right?
We can change the union into plus.
Right. Right, I can do that like that, right? Okay. So we can write it like that because the A's formed a partition of the sample space, okay? Or of the set of U. So this worked because the A's formed a partition. That's because they were disjoint and they filled out the entire set. So now we can write the probability of, we can put the pluses in there like she said. Okay, and so we can do this for any partition. So we just used A1, A2, A3, A4, but we could talk about any partition. So we can denote a partition by A sub j. So it's just a bunch of sets. And then you can rewrite Bayes' theorem, which was like this. You can rewrite it like this. Now, I'm not going to do it right now, but this is basically the same proof that we just did before for just a partition with just 2 sets. Now we have a partition with 4 sets. We could have a partition with 10 sets or 100 sets or whatever, doesn't matter. You're going to get the same basic idea. Okay? And so this is the general expression of Bayes' theorem. And it's really no different than what we did. And this is another expression of what we did. Now the only difference is here is we're using this symbol to mean the complement of A. So this means the complement of A down here. Instead of putting a bar on the top, you can also do it this way. The complement of A means not A. All right, any questions about that? Okay, we're not going to go through this. So that's Bayes' theorem, the original way we saw it. Okay, now let's go through some terminology, because as I said, there's a whole science called Bayesian Statistics. And they don't just say that it allows you to reverse the order, but that is what it does. But there's some interpretation of it that they make of this. Now, it's very, very popular now these days, Bayesian statistics and Bayesian probability. But I'm not so clear about why it is. Anyway, let's just identify some terminology here. So we have this word, we have this word, and we have this word. And with those words, we can say, this is called the posterior probability. This is called the prior probability. And this is called the likelihood function, or the likelihood. Okay? So with that terminology, we can say this is called the posterior. So the posterior, we say, is equal to what? The likelihood times the prior divided by this. If you have A equals B over C, and C is a constant, then you can say A is proportional to B, right? Does everyone agree with that? Let's say, I'm sorry, maybe I should say, if this is X and this is Z, and this is C, then we can say that X is proportional to Z. Does everyone agree with that?
Yes.
Yes.
Okay, so if this is a constant, we can leave it out and use proportional. So that's what they did here. They're saying this is going to be a constant, so just leave it out. So you just get proportional here. So this is called the posterior. We'll see why that's called the posterior in a minute. This is called the likelihood. We won't really see that, why that's called the likelihood. And this is called the prior. We'll see why that's called the prior. So anyway, if you say that, then you can write the posterior is proportional to the likelihood times the prior. That's what they have here, right? Does everyone see that? Okay, now why do they call this the prior? And why do they call this the posterior? What does the word post mean? Anybody know? You know AM and PM?
After.
Yeah. This means like after, I guess M must be some word for noon. And I think this means like anti-noon or something, or I don't know, before noon, après, maybe. In French, it's après, before. And this means post. What does post mean? Post means after in Latin. Okay? So, why do we call, so this is called the prior. P of A is called the prior, and P of A given B is called the posterior. So why is it called the posterior? Posterior. Why is it called the posterior? Because it's A given B. After being given B, what's the probability of A? So after. Okay, does everyone get that?
Oh, yes, sir.
It's the probability of A given B means after knowing B, what's the probability of A? So they call that the posterior. Okay? And so then what do they call this? If this is the posterior, then this is without being given anything. So they call that the prior. Okay, does everyone get this terminology?
Yes, sir.
So that's very common in probability and statistics. Now, this is called the likelihood. There's not even a great reason for it, and also it's complicated to explain it anyway. But even if it wasn't, I mean, it's just not a good reason to call it likelihood. But somebody decided to call it likelihood, so that's what it's called. Okay, so how much more do we have here? We don't have any more time, but what do we have here? Okay, so here's some examples of using Bayes' theorem. And then we need to review independent events. And then we need to review this other, we need to cover this other concept called conditional independence. So we'll do that next time. And then we can start on the naive Bayes algorithm. So we can finish it next week. and maybe we'll go on to something else as well. So we'll talk about how it works next week. Okay, so we spent a lot of time reviewing probability today. So that will enable us to do the Bayes theorem next time. And then we also will have to spend at least 1 week, maybe even 2, reviewing some kinds of math in order to study the neural network, in order to fully understand how a neural network works.